Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through all of the calculus you need to know for the final exam. So the final exam is going to be about 90% of it on calculus. So I've divided this part of the course into 10 skills, 10 things you need to be able to do listed on your screen. So let's start with the first one, calculating the average rate of change. So differential calculus is all about the rate of change of something, but this isn't a new concept to you. The rate of change is just the gradient, and you would have learned about that since year 8 or 9. So we use m to denote the gradient. It's just the change in y over the change in x. But you would have worked before this only using straight lines. See, straight lines are easy because the gradient is constant. The gradient is the same at every single point along the line. But let's look at a function like this. So I just drew a rough sketch of y equals x squared. So that is not a complicated polynomial by any means, but calculating its gradient would be complicated. So if we look at this region of the graph over here, what's happening is the change in y is negative, because each time we go across, each time x increases, y is going down. So the gradient of the blue curve is negative in this region. Around here, the curve is pretty flat. So when you have a perfectly flat line, a horizontal line, its gradient is 0. So the gradient of the blue curve is around 0 in this region. Now over here, the change in y is positive. As x is increasing, y is going up. So what we can see is that the gradient is different in different regions of this blue graph. In fact, the blue curve is changing at a different rate at every single point along the curve. So how are we going to quantify its rate of change? Well, one technique we can use is we can pick 2 points on the graph and calculate the gradient of the line that passes through those points. So I'll call this first point x, fx, and then I'm going to define h as the distance between the x values of the 2 points. So h is going to be this distance here, so this x coordinate here will be x plus h. So this second point, x plus h, it will meet the curve at f of x plus h. So note here, I've just used h to mean delta x, just to make the calculations a little simpler. So we have 2 points. Calculate the average rate of change. What we're doing is we're calculating the gradient of the line that passes through this point and this point. So the line that passes through this point and this point is called a secant of the curve because it intersects the curve twice. Once here, once here. So when we're calculating the average rate of change of the blue function between this point and this point, we're actually calculating the gradient of this black line, the gradient of a secant. So to calculate the gradient of this black line, we just use the 2-point formula. So we have m, the gradient, is equal to y2 minus y1 over x2 minus x1. The distance between the two x values is just h. So this here is our formula for the average rate of change of a function between 2 points. The first point is x, fx, second x plus h, f of x plus h. So let's look at a numerical example. So let's calculate the average rate of change of y equals x squared between x equals 1 and x equals 4. So in this case, h, the distance between the x values is 3. So what we need to do is calculate f of 1 and f of 4. We do that by substituting these numbers into the original equation. So when x equals 1, y also equals 1, just 1 squared. And of course, when x equals 4, y would be 4 squared, which is 16. So using the formula up here, the gradient, the average rate of change of y equals x squared between these 2 points would be f of x plus h, y2, minus f of x, which is y1, over h, the distance between the two values. So, of course, we get 15 over 3, which is 5. So 5 is the gradient of this line here, the average rate of change of the function. On average, between these 2 points, x equals 1 and x equals 4, each time we go across 1, we're going up by 5. That's on average. So now let's look at calculating the instantaneous rate of change. So I said before that the gradient of y equals x squared is different at every single point along the curve. So how do I calculate it at just one point? So let's calculate the gradient of y equals x squared at just the point 1, 1. So what I'm really saying here is I want to calculate the rate of change of the function when it's in the neighborhood of this point, when it's very, very close to this point. If I want to know how quickly the curve is changing at just this point, it wouldn't make sense for me to draw a line between here and here like I did on the previous slide. I don't want the average rate of change between 2 points anymore. I want the rate of change at just 1 point. So this was the formula that I used on the previous slide. That's when I had 2 points. What I'm going to do here is actually the same. I'm going to pick 2 points on this curve and calculate the gradient of the line that goes through them. But I want these 2 points I pick to be so close together. So mathematically, I write it like this. So remember that I use h to mean delta x, or the distance between the two x values, the change in x. So by taking the limit as h approaches 0, what I'm saying is if I want to calculate the gradient of the curve at this point, I pick 2 points, but they're so close together, their distance is almost 0. So I've picked 1 point here and I pick the other point just so close to it, their distance is basically 0. So basically, I'm calculating the gradient of this red line here. Now, because the distance between the 2 points is 0, this line is basically hitting the curve at just 1 point, 1, 1. So instead of being a secant, it's now a tangent. And that's precisely what this formula calculates. When I use this formula, I get another function. That's the gradient function. This is how we calculate the gradient of a tangent, or the instantaneous rate of change of a function. And that's what this f dash x means. It means the derivative of x, and that's the same as the gradient of the tangent, the slope of the curve, the instantaneous rate of change. They all mean the same thing. So let's use this formula for the function fx equals x squared. So if that's f of x, to write what f of x plus h is, I just take this here and replace x with x plus h. So all I've done from here to here is take x and replace it with x plus h. So expanding the brackets, I get x squared plus 2xh plus h squared. So I'm going to substitute all of this into the formula above. So then I have f of x plus h, which is all of the stuff I just wrote, minus f of x all divided by h. So when you're finding the average rate of change, you just do this part here in blue. But when I'm finding the instantaneous rate of change, which is the derivative or the gradient of the tangent, I need to take the limit as h approaches 0. And this is equal to the first derivative or gradient of the tangent. So now I'm just going to make this a little easier to work with. Of course, we have x squared minus x squared, so I can just get rid of those. So now what I'm left with is an expression that has h's in each of the terms. Now, I can't just substitute h equals 0, top and bottom, because then I'd be dividing by 0. So instead, before I substitute h for 0, I'm going to divide. I'm going to divide 2xh by h and then h squared by h. So that gives me limit as h approaches 0, 2xh divided by h is just 2x, and h squared divided by h is just h. So now I can substitute h equals 0 into this expression here. There's nothing wrong with that. So then the h goes away and I'm just left with 2x. So the derivative of fx equals x squared is just 2x. So what that means is the gradient of this function is 2 times whatever the x value is. So at x equals 1, the gradient of this tangent is 2 times 1, which is 2. The rate of change, the instantaneous rate of change at, say, x equals 4, would be 2 times 4, which is equal to 8. If I were to draw a tangent that hits the curve at the point x equals 4, its gradient would be 8. So when we differentiated a function, we got another function. This is the gradient function that tells us how to find the rate of change of this function at any point. So this formula here is known as first principles. So that's what we're actually calculating when we calculate the derivative. But we don't always want to use first principles because it can take a long time. So let's look at some shortcuts, some easier ways to differentiate functions. So rather than use first principles, which takes a while, when we're differentiating polynomials, we can just use these 4 rules. Now, they're written in a complicated way, but they're actually very simple. First rule says if you're differentiating x to the power of something, you move the power to the front, so times it, and then you decrease the power by 1. The second one says if you're differentiating 2 functions that are added together, you can just differentiate them both and then add their derivatives together. So the third one says if you're differentiating a constant times a function, you can just times the derivative of the function by that constant. And the last one says if you add a constant to a function, you don't change its derivative. So it probably doesn't make heaps of sense. Let's look at some examples. So let's have something like y equals x to the power of 5, and I want to differentiate it. So I'm going to use the notation dy dx, f dash x. It all means the same thing, means first derivative. So to do this, I move the power to the front, and I decrease the power by 1. How easy is that? So let's differentiate this function here. So this time I'm going to use f dash x, which means the same as dy dx. They both mean first derivative. So using the rules, for 4x cubed minus 4x plus 1, I can differentiate each of these term by term. So starting with this term, 4x to the power of 3. So what I can do is leave the 4 alone and just differentiate x cubed. So to differentiate x cubed, I move the 3 to the front and decrease the power by 1. So when I'm differentiating minus 4x, note that that's minus 4x to the power of 1. I can still use the same idea. So what I'm going to do is leave the minus 4 alone at the moment, and then I'm going to do the same thing as I've been doing. I'm going to move the power to the front and decrease the power by 1. So I actually get minus 4 times 1x to the power of 0. Now, the last rule here tells us when we're differentiating a constant, it just vanishes. I don't need to do anything with this in the derivative because adding 1 to a function doesn't change its derivative. So that one's just gone. I don't even worry about it. So, of course, I can make this easier to work with. 4 times 3 is obviously 12, so I get 12x squared. X to the power of 0 is just 1. So I just get 12x squared minus 4. So as I said on a previous slide, the derivative of this function is another function. I can substitute values of x to find the gradient of this function at those points. So we can also use these rules for derivatives for functions like these which actually are not polynomials. The reason we can use those rules here is I can write each of these terms as a power of x. So 1 on x is just x to the power of minus 1, and the square root of x is just x to the power of a half. So now that I've got it in the form where it's just x to the power of something, I can use any or all of these rules. So to differentiate this, I move the power to the front and decrease the power by 1. Same with the other one. So I'm going to leave the 2 alone. I'm going to move the power to the front and then decrease the power by 1. So a half minus 1 gives me negative a half. So just making this easier to work with, this would be minus 1 on x squared plus 1 times x to the power of minus a half is 1 on square root of x. And there's my answer. This is the derivative function of this one. So for the last example, differentiate this function here. You might think, okay, we haven't gone through how to differentiate quotients. But what we can do a little trick to make this in the form where it's just lots of x's to the power of something. So the trick we're going to use, we're going to divide. So we're going to divide x by x squared. And that gives us 1 on x. Then we divide minus 3x cubed by x squared, and we just get minus 3x. So I haven't actually differentiated yet. That was just me making y easier to work with. So now I'm going to differentiate this. So I'm going to use the terminology y dash dy dx, f dash x all mean the same thing. So I know the derivative of 1 on x is minus 1 on x squared, just using the power rule. And the derivative of minus 3x is just minus 3. Then I'm done. So let's now move on to finding the equation of a tangent. So we're going to find the equation of a tangent to this curve at the point where x equals minus 1. So as I previously told you, the derivative, so in this case y dash, is the gradient of the tangent. So if I differentiate y, I get y dash equals 12x to the power of 3 minus 5. Remember, this 6 just vanishes when we take the derivative. So if x equals minus 1, then y dash would just be 12 times minus 1 cubed minus 5. So if you put that in your calculator, you get minus 17. So what I've actually calculated here is I've calculated the gradient of this curve at the point x equals minus 1. Remember, the gradient of the curve, what I really mean is the gradient of the tangent to that curve. So the question though asked us to find the equation of the tangent. So I found the gradient. So what we do to find the equation, we note that the tangent is just a straight line. The equation of any straight line is y equals mx plus b, where m is the gradient and b the y-intercept. So we've actually just found the gradient, so I'm going to substitute m for minus 17. Now x and y come from the point. So we know that the tangent at this point, x is minus 1. To find the y value at this point, I don't substitute in here, I substitute into the original function. So substituting in, I get that the y value is 14. So now I'm going to take this equation, I'm going to substitute m for minus 17, x for minus 1, and y for 14. I'm going to substitute all of that to find what b is. So I get y equals m times x plus b. So I get 14 is equal to 17 plus b, so that clearly gives me b is equal to minus 3. So I found m and b. That means the equation of the tangent is y equals gradient times x plus y-intercept. And then we're done. So let's move on to determining when a function is increasing or decreasing. So when we speak of a function increasing or decreasing, we're really talking about what is happening to the y value. So we're always looking at a function going to the right as x is increasing. Is y increasing? Or as we go to the right, is y decreasing? That's what we're talking about here. So a function is increasing if its gradient is positive. If it's increasing, the curve is leaning to the right, and the first derivative is positive, because remember, the gradient and the first derivative are the same thing. So on the other hand, if a function's decreasing, it's leaning to the left and its first derivative is negative. If it's neither increasing nor decreasing, then the function is stationary. So that means that the curve is sort of flat and the gradient first derivative is equal to 0. So let's look at this red function down here. So this is the graph of just some function I'll call fx. So we obviously can't calculate the derivative of fx because we don't know what fx is, but we can still tell when the function is increasing, decreasing, or neither. So what's happening here is the function before this point x equals a is leaning to the right. The y value is going up, and then it stops at a, turns around. Now it's decreasing to b. At b, it stops and turns around. It starts increasing again. It sort of stops at c and then continues increasing. So for this function, it's increasing on the interval where x is less than a. It's also increasing on the interval here between b and c, but it doesn't include those values. So the way we write that, we write b is less than x is less than c. This says colloquially that x is between, but not including b and c. And then it's also increasing when x is greater than c. So this function is increasing on 3 different intervals. So the function is decreasing when x is between but not including a and b. So we write it as a is less than x is less than b. So that's when the function is going down, leaning to the left. And the function here is stationary at 3 points. It has 3 stationary points. One of them at x equals a, one of them at x equals b, and one of them at x equals c. So even though I can't actually calculate the first derivative, I know the first derivative would be 0 at this point, and this point. So this is what we call a maximum turning point because this is the maximum value in this area. This is a minimum turning point because this y value is the lowest value in this area. C is what we call an inflection point. We haven't done too much work on that, so don't worry too much about them. We need to be able to find stationary points and classify them as maximum or a minimum. But the thing is, when we're given a function, we don't always want to graph it because that would take a long time. So let's look at using the first derivative test to determine when a function is increasing, decreasing, or stationary. So we're now going to look at where this function x cubed minus 3x minus 2 is increasing, decreasing, or stationary. So what we're going to do here is we're going to differentiate this function here, find where the derivative equals 0. That will tell us the stationary points, and then we'll use the first derivative test. So differentiating this function up here, I get f dash x equals 3x squared minus 3. Now I want to find where this is equal to 0, so I can just do a simple factorization for this here. So using the null factor law, the derivative will be equal to 0 when either the first bracket or the second bracket equals 0. So of course that means x is equal to 1 or minus 1. That means the stationary points of this function, there's 2 of them. One at x equals 1 and one at x equals minus 1. So what I do now that I've found the stationary points is I draw up a table. So I put in the 2 stationary points, minus 1 and 1, and I need to pick x values on either side of these stationary points. So I could pick x equals minus 2, 0, and 2. And what I'm going to look at is I'm going to look at whether the derivative is positive or negative at these points. That will tell me whether the curve is leaning right or left at these points. It will allow me to determine whether each of these stationary points is a maximum or a minimum. It'll also tell me when the function is increasing or decreasing. So I know that if I substitute minus 1 or 1 into the first derivative, I'll get 0. That's exactly what I just found out. So now I'm going to substitute x equals minus 2 into the first derivative. So if I substitute minus 2 into this, make sure you use brackets when you substitute a negative. I actually get a positive answer. I get positive 9. If I substitute x equals 0 in the first derivative, I get negative. I get negative 3. If I substitute x equals 2 into the first derivative, I again get positive 9. So what is all this telling us? Well, it's telling us when x is minus 2, when x is less than this first stationary point, the first derivative is positive. That means the function is increasing and leaning to the right. It's telling us that the derivative is negative between these two stationary points, so the curve will lean to the left. And then it tells us that the first derivative is positive after this stationary point. The curve will again lean to the right. So at the two stationary points, we know it's flat. This is what the curve is doing. It's increasing until it gets to this first stationary point, stops, turns around, then becomes decreasing, stops, turns around again, and then it starts increasing. So we have all the information we need to know to answer this question. So, on what intervals is this increasing? It's increasing before the first stationary point, so for x is less than -1, and also after the second stationary point. So it's increasing when x is less than -1 or greater than 1. We can see that it's decreasing between the two stationary points. So it's decreasing on the interval -1 is less than x is less than 1. Remember, we read that as x is between -1 and 1. And we know that it is stationary at those two stationary points, at x equals -1 and at x equals 1. So this is also going to be very useful information if we're asked to graph this function, which we will now do. So we're going to graph the function fx equals x cubed minus 3x minus 2. Whenever you're asked to graph a polynomial, you'll find these three things. The y-intercept, which is really easy, the x-intercepts, which may take a bit of work, and the stationary points, and also the orientation, which we actually just calculated. So for this function here, the y-intercept's easy. The y-intercept is the y value when x is equal to 0. So if x was equal to 0, fx would just be minus 2. Note, fx and y are the same thing here. So the y-intercept here is just y equals minus 2. So to find the x-intercepts, what you need to do is find the roots. You need to find the values of x that make this polynomial equal to 0. So what you can do is actually just graph this on your graphics calculator and you'll find the x-intercepts. If you want to do it by hand, remember we need polynomial long division. You need to find a root first and then use polynomial long division. You can find that first root from your graphics calculator, or remember you try positive, negative factors of the constant term. So one of the roots of this function here is x equals minus 1. If you substitute x equals minus 1 into this expression here, you get 0. So since minus 1 is a root, that means x plus 1 is a factor. Now you can use polynomial long division if you want. X squared minus x minus 2, and you can factorize that quadratic really easily. You just find two numbers that multiply to minus 2 and add to minus 1. So after we factorize it, we use the null factor law to find what values of x would make this equal 0. So of course those two numbers would be x equals minus 1 and x equals positive 2. So they are the two x-intercepts. But note that this minus 1 is repeated. It's what we call a double root. So when you have a double root, the function sort of bounces off that root. A double root means that the intercept, the x-intercept, is also a turning point. So it'll either look like this or like this, where we have the axes here. So this only happens when the intercept is a double root, when it is repeated. There are two of those factors that give us a solution x equals minus 1. So we found the y-intercept, we found the x-intercepts, and it turns out we did all the work on the previous slide to find the stationary points and also the orientation. So we found on the previous slide that x equals minus 1 and x equals 1 are both stationary points. We found that x equals minus 1 is a maximum turning point, x equals 1 is a minimum turning point. From this, we can also get the orientation. When I say orientation, I mean what happens as x goes to positive or negative infinity. So we have all the information we need to start graphing this. So firstly, let's start with what's really easy, and we'll mark the y-intercept. Now we'll also mark the x-intercepts here. So we don't know which way the curve is going. It could go like this or whatever. We don't know without this table. What this table is telling us is that the function is increasing before this first stationary point here. So it's going to increase and then come up to this first stationary point here. Then it's going to stop and turn around, start decreasing, and eventually it's going to go to the second stationary point, stop, turn around, and this tells us that after that it's increasing. So when x equals 1, we need to know the y value of this turning point. We need to know, is the turning point down here or up here? So we know that the first turning point, the first stationary point, is at -1, 0. The second one, if I substitute x equals 1 into this expression here, I get y equals -4. So the second stationary point is down here at 1, -4. So what's going to happen with this graph? Remember, it's increasing before the first stationary point. So it's going to be increasing like this. And then it hits this x-intercept. It stops and turns around. Now it's decreasing. It's going to go through the y-intercept until it gets to this turning point here, stops, turns around again, and the table tells us it's just going to be increasing thereafter. So that's what the graph is going to look like. Note here at -1, there's that double root situation we were talking about. All right, there we are. We're done. Let's move on now to antiderivatives. So when I anti-differentiate a function, I do the opposite of when I'm differentiating. So if I start with something like x squared, I know that if I differentiate that function, I get 2x. Remember, of course, that differentiate means finds the derivative. But if I go the other way to find an antiderivative, I'm saying what function, when I differentiate it, would give me x squared. So that function is x cubed on 3. Because if I differentiate x cubed on 3, I get x squared. And that's exactly what calculating the antiderivative does. It says, find a function so that when you differentiate it, you get what I started with. So let's start with something like x to the power of n. So I know when I differentiate it, I get n, move the power to the front, and then decrease the power by 1. So when I anti-differentiate, what I'm going to do is the opposite. Instead of decreasing the power by 1, I'm going to add 1, increase the power by 1. And instead of multiplying, I'm going to divide. So I'm going to divide by that new power. And that's the formula I'm going to use to anti-differentiate polynomials. So note, this symbol here means integral or find the antiderivative of. So if I want to find the antiderivative of x to the power of n, I just increase the power by 1 and divide by that new power. So let's look at a few examples of finding the antiderivative. So let's say I wanted to find the integral or the antiderivative of x to the power of 4. So I would just increase the power by 1 and I would divide by that new power. So when I'm finding an antiderivative, I need to write this here plus c, plus a constant. The reason is, remember that when we differentiate, adding a constant doesn't change the derivative. So that means that if I were to differentiate x to the power of 5 over 5, or x to the power of 5 over 5 plus 1, these two functions here and here would both have the same derivative. If I differentiate this, I get x to the power of 4. If I differentiate this, I get x to the power of 4. In fact, it wouldn't matter what number I added here. If I added 5 and differentiated, I'd still get x to the power of 4. If I had x to the power of 5 over 5 minus 9, if I differentiate that, I get x to the power of 4. We need to write this plus c here, add this constant, because I can add any number to x to the power of 5 over 5, and if I differentiate it, I would get x to the power of 4. So let's calculate the antiderivative of this polynomial here. So just like when differentiating, I can do each term one by one. Find the antiderivative of this, and this, and then just add them together. So let's start with 4x cubed. So again, just like differentiating, when you have a constant out the front, you can sort of just ignore it. So what I mean by that, I'm just going to leave the 4 alone, write it, and I'm going to find the antiderivative of x cubed. So to do that, I just increase the power by 1 and divide by the new power. So that's the antiderivative of 4x cubed. Now I'm going to do of minus 3x. So remember, minus 3x is the same as minus 3x to the power of 1. So again, I'm just going to write the minus 3, leave it to the side for the moment. I'm going to increase the power of x by 1 and divide by that new power. So for 5, this is the same as 5x to the power of 0. So what I can do is I can leave the 5 alone, but the antiderivative of x to the power of 0, I'm going to do the same thing I've been doing. I'm going to increase the power by 1 and then divide by the new power. So remember, when I do take the antiderivative, I have to add c, some constant here, to represent that I can add any number I want. If I differentiate this, I will get this. So just making it a little easier to work with. Of course, here the 4's cancel out. So I'm just left with x to the power of 4 minus 3x squared on 2. Of course, 5 over 1 is just 5, plus 5x plus c. If I take any function of this form with any constant here and I differentiate this, I get what I started there. All right, let's now move on to some problem solving. So let's look at this question here. So the cost of producing X units of a drink is given by this function here. C is the cost in dollars. So we're asked to calculate dc dx, the derivative of this cost function, evaluate it when X equals 100, and interpret its meaning. So let's start by calculating the derivative. So I can call it C dash because C dash and dc dx mean the same thing. So we're differentiating C with respect to X. The derivative of 3x is just 3. Remember, when differentiating, constants just vanish, so I don't need to worry about that. The derivative of minus 0.01x squared. So I times it by 2, and I decrease the power of x by 1. So if I want to know what the derivative is when x equals 100, I simply substitute x equals 100 into here. So I would get 3 minus 2, which is 1. So that's when x equals 100. So I found that when x equals 100, the rate of change of c is equal to 1. So what does that mean? So that number here, 1, tells me that the rate of change of the cost when x equals 100 is 1. That means the cost, because it's positive, increases by $1 when I produce the 100th unit. In layman's terms, that means that the 100th unit costs $1 to produce. We can't say anything about the average cost here. We can't say anything about what, the second unit costs to produce. This only tells us what the cost is when x equals 100. All right, let's now look at doing some straight line motion problems. So we're going to look at objects moving in a straight line. So usually we use y or x to mean the position. So the derivative of the position with respect to time, the change in position over time, is equal to the velocity, and the change in velocity over time is equal to the acceleration. So note, in these problems we're using velocity and not speed. So speed always has to be positive. The velocity of an object can be positive or negative. That's really the only difference between speed and velocity. Speed's always got to be positive, velocity can be negative. When you have a negative velocity, it just tells you the speed it's going, but in a different direction. So like you'd have a positive velocity if you were traveling to the right, a negative velocity if you were traveling to the left. That's the only difference between velocity and speed. So let's look at a question that we could solve with this. So let's look at this question here. Rocket fired 2 meters above ground level, initial velocity 30 meters per second. The rocket has a constant acceleration of minus 10 meters per second squared. What is the maximum height reached by the rocket? So this would be a really easy question to do if we had the position of the rocket, its height above ground level, if we had a function for that. So we know that the acceleration is minus 10 meters per second. So the acceleration here is just constant at minus 10. So from this, we can use calculus to figure out what the velocity is. So to find the velocity, remember I said that acceleration is the derivative of velocity? So let's go the other way. That means velocity is the antiderivative of acceleration. So we're going to have velocity is the integral of acceleration. So the integral of minus 10 is actually going to be minus 10, and it's going to be t, because acceleration is the derivative with respect to t, with respect to time. So remember, when we're doing antiderivatives, we have to also add a constant. Now, in previous slides, we didn't find what this constant is, but in this question, we've been given some extra information so we can find what c is. The initial velocity is 30 meters per second. What that means is when t is equal to 0, because that's what it means by initial, then v is equal to 30. So all of that means that c, the constant, has to actually be equal to 30. So the velocity of the rocket is 30 minus 10t. 30 minus 10 times whatever the time is. So note that t would be in seconds, because meters per second for velocity, meters per second squared for acceleration. So that's what the velocity is. So we can actually find what the position y is in terms of t. So to find that, all we're going to do is take the integral of the velocity. So the integral of minus 10t, so remember we're going to increase the power of t by 1, and we're going to divide by that new power. So then the integral of 30 is just going to be 30t. Once again, I have to add a constant. Now, again, I can find what this constant is by the information in the question. I was told that the rocket was fired 2 meters above ground level. That means it started at 2 meters above ground level. That means that the initial height of the rocket was 2. So that means this constant here, I can rub out and I can replace it with 2. So this function here tells us the height of the rocket above ground level after a given time t. Of course, we can make it a little easier. Instead of having minus 10 over 2, we can write that as minus 5t squared. So this is the height after t seconds. So what would be the maximum height reached by the rocket? Well, we know the derivative of y is just the velocity. So the velocity would equal 0 when minus 10t plus 30 equals 0. It would equal 0 when t is equal to 3. That means after 3 seconds, because minus 10 times 3 plus 30 is equal to 0. So when t equals 3, I just substitute t for 3 into this equation here. So substituting that in, I actually get y equals 47. So that means the maximum height reached by the rocket is 47 meters above ground level. Now, we weren't actually asked to graph it, but I'm going to quickly graph this. So graphing this function here, I get something that looks like this. So the rocket is going up, up, up. It's increasing its height. Then it stops. It stops increasing its height, so the velocity here would be 0. Then it turns around and starts coming down. Note, this isn't actually the path of the rocket. The rocket is moving in a straight line. It's just going up, stopping, and then coming down. This is just a graph of its change in height with respect to time. All right, let's look at one more problem now involving optimization. So let's look at this question here. A 1 meter by 2 meter sheet of cardboard has squares cut out of each of its corners. We then fold the sides of this to make it a box, and we want to know the maximum volume that could be contained by this box. So let's start first by drawing a diagram. So we have a sheet of cardboard like this that's 1 meter by 2 meters. And we're going to cut out squares from each of the corners. We don't actually know how big each of these squares is. So what I'm going to do is just call the side length of these squares x. So each of these is an x by x square. So you might be thinking, well, what does this have to do with calculus? Well, because we're talking about maximizing, hopefully straight away you think we're going to get a function for the volume. We're going to find its maximum value by finding where its first derivative is equal to 0. So what would be the volume of the box? So we're going to cut out these squares and then fold up these sides here and this side here, so that it's a box. So what we have is that this dimension along here would be 2 minus 2x. And then we have that the shorter dimension would be 1 minus 2x. So that's what the base of the box would be. It would have an area of 1 minus 2x multiplied by 2 minus 2x. So then the height of this box when it's folded will just be x. This will become the height. So this is what the volume is in terms of x. So what we want to do is differentiate this and find where the first derivative is equal to 0. So we haven't really gone through rules for differentiating functions like this in factorized form. So unfortunately, we're going to have to expand this here. We'll start with the brackets. So the idea when you're expanding something like this, you know how to do that. We multiply everything in the first bracket by everything in the second bracket. So that's what FOIL basically does. So F is the things that come first in each bracket. Then O, the things on the outside of each bracket, 1 times minus 2x. Then I is the insides, minus 2x times 2. And then lasts. Minus 2x times minus 2x gives us positive 4x squared. Of course, I can make 2x minus 2x minus 4x easier to work with by just writing minus 6x. Okay, so now what I do is multiply everything in the brackets by x. I get 2x minus 6x squared plus 4x cubed. That is my function for the volume. So to find where this is a maximum, I'm going to have to differentiate it. So the derivative of this, so I'm going to differentiate 2x. The derivative of that is just 2. Derivative of minus 6x squared gives me minus 12x. And the derivative of 4x cubed gives me 12x squared. So now I have to find where this derivative is equal to 0. This is a quadratic, so I'm going to use the quadratic formula. So using the quadratic formula of x equals minus b plus or minus square root of discriminant over 2 times a. So you get two solutions here, both of them irrational. So one of them's about 0.79 and the other about 0.21. So we've got two answers here. These correspond to the two turning points of this function here, but we don't know which of them is a maximum. So one of them will be a maximum and one of them will be a minimum. So over here, we don't need to go through the full first derivative test. Let's just substitute each of these in. So the thing is, if I substitute x equals 0.79, what's going to happen is I'm going to get a negative answer. The volume in that case is about minus 0.2. If I substitute x equals 0.21 into the volume formula, I get about positive 0.2. So clearly, this one here is larger. That will be the maximum. This will be a minimum, and you can't actually have that. And of course, that makes sense. I can't have x being 0.79 because that would mean that 0.79 is 1.58. It would add to larger than this 1 meter dimension. That's why I got this weird impossible answer. But if I have 0.21, then this dimension here will be 0.58, and this will be 1.58, and then the volume will be about 0.2. So the dimension of the squares that maximizes the volume is about 0.21. Each of these squares should be about 0.21 by 0.21. All right, sorry for the long video, but thank you so much for tuning in. Best of luck studying for the exam, but you're a superstar. You'll ace it. This has been the luckiest maths teacher in the world. Have a great day.